All right, so we are on 2B.4 Introduction to Inverse Functions, Part 2, reflecting on inverse functions. Okay, so let's dive in. What is an inverse function? So by now we should understand an inverse function in math means that it undoes the action of the original function, essentially reversing the input and output. If a function If function f takes x to y, its inverse is going to take y to x. Basically, you're switching your input and your output. So you're switching your independent and dependent variable. So if you remember from Algebra 1, your Algebra 1 teacher may have taught you Dixie-Royd. So Dixie and Royd. You're probably like, who and what are Dixie and Royd? Dixie and Royd are how we remember synonyms for domain and range. What things mean what? So you have your domain is input, your x value, and your independent variable. Okay. Your range is your output, your y value, and your dependent variable. Okay. Now, this is when you're in f of x. So when you have f of x, this is how your domain and range are set up. When you're doing the inverse, we're basically saying what was domain, they're now going to switch for your inverse. So for your inverse, you're now starting with, right, in purple. You're now saying what was my domain is now my range. What was my input was now my output, and they're switching. So again, you're switching your X's and Y's. All right. So when two graphs are reflections of each other over the line y equals X, then they are said to be inverses of each other. Okay. It's a reversal. It swaps the roles of the input and the output, your domain and your range. So we're going to start with an ordered pair. An ordered pair can also be listed as a table. It's the same idea. So we have this ordered pair here. If I was to turn this ordered pair into table, it would look like so. We would have 4, -3. We have 2, -1, 7, 0, -1, 4, 2, and 10. Okay. Now, when we're writing the inverse of this, the inverse is saying that our X's and Y's are switching roles. So X's and Y's are switching roles. What was our X's are now our Y's, and what was our Y is now our X. And that's how we write the ordered pair. Okay. So now that we understand that, when we make our new set, our new solution, don't make fun of my braids. Oh, that's a pretty decent one for me. Therefore, it becomes -3, 4. Then we have -1, 2. Then we have 0, 7. Then we have 4, -1. And then we have 10, 2. And that would be our new set. Okay. And this is just a relation. I want to emphasize that it's a relation because all functions are relations, but not all relations are a function. And so this one would not be a function because now I have repeating. I'm sorry, this would be a function, not just a relation, because I now no longer have any repeating x values. In the beginning, I had repeating x values, which made this not a function. But when I found the inverse is a function. Okay. All right. Now using a graphing utility, we're going to create a table of values in table 1 for the equation given. We're going to plot the points. We're going to switch x and y coordinates. We're going to record, and we're going to plot the points. So graphing with and without a graphing utility. First, we're going to start without a graphing utility, and then we're going to look at it from the graphing utility point perspective. So here we have y equals 2 to the x, and we've talked about it before. This is an exponential function, right? Our x values are our power. So if let's just say we started off with -1, then we have 0, 1, 2, 3, and 4. Well, let's not do those. Let's switch that up really quick. We're going to do -2. 4 won't be within. -2, -1, 0, 1, 2, and 3. So 2 to the -2 is what we're asking ourselves. And as we talked about before, when you have a negative exponent, that means that you're still going to find the power 2 squared, which is 4. But because it's negative, that means it belongs in the denominator. Okay. 2 to the negative 1 is going to give us 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the 1 is going to give us 2. 2 to the 2 gives us 4. 2 to the 3 gives us 8. Okay, so this is our y, our original function. And when I plot those points, we end up at doom, 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 2, 3, 4. Okay, I didn't want to stay. So we have all of our points plotted. And for exponentials, remember that they have a horizontal asymptote, which means that we have that boundary line that we can't cross, right? This boundary line at y equals 0. Okay, so we are, and we keep going. So that is our original. After the original, we're now going to graph our inverse. So notice I'm going to put a negative on that y. This is going to be our inverse, meaning that I'm switching my x and y values. So my input is now 1/4, my output is -2. My input is now 1/2, my output is -1. Input is 1, output is 0. Input is 2, output is 1. Input is 4, output is 2. Input is 8, output is 3. Okay, so I'm going to go to 1/4, and at 1/4, I go down to -2. It's pretty good just to make. I'm going to go to half, be at 1. I'm going to go to 1. I'm going to be at 0. I'm going to go to 2, and I'm going to be at 1. I'm going to go to 4, and I'm going to be at 2. I'm going to go over to 8, and I'm going to be at 3. Okay? Now, remember how we talked about that horizontal asymptote? If my asymptote was horizontal, the inverse of that is going to be a vertical. So now we have a vertical asymptote. At x equals 0. So we have this at x equals 0. And we're going to follow it. And, your teacher is drawing to the best of her abilities, which isn't half bad. Okay. And that is my inverse. And as we've learned, what is the inverse of an exponential function? If I have this, its inverse is a log function. Logarithmic function. I hope I spelled that right. Our logarithmic function would be log base 2. And we're going to of x equals our inverse, right? That's our inverse function. And what I want you to pay attention to is that they are a reflection over the y equals x line. So we're going to pretend that I drew these like super duper perfect, and it's a reflection over the y equals x line. Meaning that if I was able to unfold along this line, they would overlap each other. Okay? So we see that visually, graphically, and we're able to do it because we understand the idea that if I can graph one, I can graph the other by switching my x's and y's. Next here, we have 2x minus y equals 5. And for this one, we're going to use technology to do it with us, okay? Just to model how to do it with a graphing utility. So the first thing, though, we're going to have to do is we're going to get y by itself so that we can graph it and be able to use the graphing table. If you put this in Desmos, it will graph it, but it will not provide a table for you. In order to get the table, you have to get y by itself. So in order to get y by itself here, I am subtracting my 2x, and then I'm dividing by -1, if we remember that correctly. So first I'm going to subtract 2x. And what I do to one side, I'm going to do to the other. So we're left with -y equals 5 minus 2x. After I subtract 2x, I'm going to divide by -1. Divide everything by -1. Dividing everything by -1 essentially is going to change their sign. So we're left with y equals a negative divided by a negative is a positive. So we have positive 2x. A positive divided by a negative is going to be a negative. So we have y equals 2x minus 5. And that is our original function, right? Y equals 2x minus 5. So we're going to graph y equals 2x minus 5. Let me open Sylvie. Hey, girl, hey. All right, here's Sylvie. So I'm going to go to y equals, and I'm going to put in 2x minus 5. Again, you can do this on Desmos as well. So I hit graph, and we'll see that it creates a linear equation. I have a linear equation that goes through -5 and has a slope of 2. What we're going to do is we're going to find some points to graph. So we're going to, key points that we want to make sure we have are our x-intercept, and you can kind of see our y-intercept. I mean, our y-intercept, and you can kind of see what our x-intercept is. But to make sure we know what our x-intercept is, we're going to hit second, trace, and we're going to look for our 0, which is our x-intercept. Again, on Desmos, you would just click, which is okay. On TI-84, we're going to go below and above our x-axis, and it's going to tell us it's at 2.5. So we were correct. So we know that 2 of our primary points on here are going to be our intercepts. So we have our 0 at -5, and we have -2.5 is our 0, our x-intercept. Okay, we're going to look at some other points from our table. So to get to our table, I press second graph. And I'm going to, just so that I can have a balance of problems, I'm going to use -1. So I have -1, and that puts me at -7. I have -2, and it puts me at -9. And I'm going to use some positives. So I have 1, that puts me at -3. And I have 2, and that puts me at -1. Okay, so now I have my points. I can plot, and I can sketch, and I can count it out. So I'm at 1, 2, 3, 4, 5. I know I'm at a half, but I can also count up using my slope. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. Rise, run, rise, run, rise, run. Okay? Fall, crawl, fall, and crawl. And I'm going to do my very, very best to connect all of my dots. All right. So here is my original, my y. All right. Now it asks me to find my inverse. So that other table is for my inverse. So look, this is going to be my inverse table. I know for my inverse table that it's going to be a change of my x's and my y's. So I have -5, 0. I have 0, -2.5. I have -7, -1. -9, -2. -3, 1. -1, 0. I can plot these points. So I can go to -5, 1, 2, 3, 4, 5, and I'm at 0. I can go to 0 and go to -2.5. I can go to -7 and go to -1. Did I go? Oh, this is positive, and y'all just let me do that. I was like, something did the math was in math, and did y'all see my confusion? Who did that? Who does that? Weirdos. Tell you, weirdos. Let's try that again. 0 and positive 2.5. And then we were at -7, -1. And I could keep going. And we're at -9, -2. We're at -3 and +1. We're at negative. Guys, y'all just be letting me write anything. Granted, no one's here to tell me. It's me. I'm the problem. We're at -1, 2. And then we're at, it would help if I go over. This is a sign that I should be leaving. Okay, so looking here, you can see that our slope has changed, right? Our slope is a little different. So when I want to write the inverse model here, my slope is now I rise 1 and I run 2. I rise 1 and I run 2. So my slope is now 1 over 2, and my y-intercept is at +2. 2.5. And that's my inverse model. To draw this out a little further, I'm going to rise 1, go over 2, rise 1, go over 2, rise 1, and go over 2. Do you notice that my lines, I had to be quiet for a second so I could try and draw as straight as possible. Maybe I'm just gonna keep going a little further so I can try to find a goal to get to. Sometimes it helps. There she goes. So here is my inverse, okay? Notice that they intersect. The points where they intersect, those are our on the imaginary line. So that's why they intersect there. So this intersection is taking place on that invisible y equals x line of reflection. And that's when they'll intersect them, if they do intersect. Okay, and we were able to figure out our equation of the line by using our prior knowledge about linear equations. So hopefully that wasn't too terrible. Okay, up next is example 4, and you have y equals x squared. For y equals x squared, please pause, choose which way you would like to do it. You can use technology or not use technology, but I would like for you to pause and try. All right, welcome back. So we have y equals x squared, right? And so for y equals x squared, we want to find out what is the inverse of this. So we're going to start off by creating our initial points. For y equals x squared, I'm going to use -2, -1, 0, 1, 2, and 3. And that's going to put me at 4, 1, 0, 1, 4, and 8. So I'm going to plot it. I have do. And just for filling out the graph, I'm going to go ahead and go up 1, 2, 3, 4, 5, 6, 7, 8, and I need 9. 4, 5, 6, 7, 8, 9. Now we do it on the other side because quadratic is symmetrical along the x-axis, y-axis. Pretend that I touched that point. We got imaginations. All right, so there is my y. Now, I'm going to switch my x and my y to create my inverse. So we're now at 4, -2. We're now at 1, -1. We're now at 0, 0. We're now at 1, 1 still. We're now at 4, 2, and we're at 8, 3. Okay. So I'm going to go to 4, -2. So 1, 2, 3, 4, down 2. I'm going to go to 1, -1. I'm going to go to 0, 0. I'm going to go to 1, 1. I'm going to go to 4, 2. 1, 2, 3, 4, up 2. And I'm going to go to 8, 3. And I'm going to, for symmetry purpose, go to 8, -3, because that would also be reflected, right? Now, as you can see, we created our inverse. It's an inverse relation. And why am I calling it an inverse relation? Because yes, it's an inverse because we switched our input and our output, but it's a relation because I'm going to use a different color. We have repeating x values all along, right? This is an example of repeating. These are repeating. These are repeating. It's repeating after 0, 0, 0, 0. So right now, this is not a function. Our inverse exists. So we have our inverse, but our inverse is not a function. Okay? And we're going to talk more about this. In order for this inverse to be a function, we have to have what's called a restriction on our domain. And currently we do not. Okay. If we wanted this to be an inverse, our domain would need to be restricted. By restricting our domain, that means that we would have to say that we're only looking at our x values that are greater than or equal to 0. If I'm only looking at my x values that are greater than or equal to 0, I'm going to go to the highlighter. That means that I would only have used this side of the quadratic. And if I only use that side of the quadratic, then when I reflect over the y equals x, then I would be only focused on these pieces. And then therefore, it would be a inverse function. Okay. The inverse of a quadratic, which we all know, is the square root. The inverse action to taking the square of something is to take the square root. So the inverse function would be the square root function with a restriction. And that is it for that section.